Welcome to lecture 34, where we discuss other criteria for positive series. Let's start with the criterion of asymptotic comparison. This is a slight variation of the criterion of pure comparison. It only focuses on the sequences when they go to plus infinity. Now, there are two versions of this criterion. We'll start with the standard case. Let's first introduce the setting to the criterion. Let's suppose that AN and BN are two real sequences. And these sequences are such that AN is larger than or equal to 0 for every natural number. So it is just a sequence of positive or null numbers. And Bn is instead a sequence of strictly positive numbers, real numbers. So if we have that the ratio An divided by Bn, which is a new sequence, is convergent to a positive real number L, then we can conclude that if the series built on top of Bn diverges, then the series built on top of An diverges. So if one diverges, the other diverges. And the same thing happens if the series built on top of Bn converges, then we can conclude that the series built on top of An converges as well, possibly to a different limit, but we know that we don't care about the numerical value of the limit, we only care about the type of behavior. So we are saying that in the first case, if the series sum Bn is of type 2 or 3, then we can conclude that also the sum of An is of type 2 or 3. If instead the sum of Bn is of type 1, also the sum of An is of type 1. So we have a one-to-one mapping, between the behaviors of the two series. So the idea behind this criterion is that suppose that we need to study sum of An, and we are struggling to find out what is the behavior of sum of An. If we find another series sum of Bn such that An over Bn will converge to a positive number, then we know that the behavior of sum An is exactly the same as this behavior of sum of Bn. Okay, so let's provide a proof of this criterion. And the proof is the following. Now, remember that we have in the hypothesis of applicability of the criterion that An over Bn will converge to a positive L. So L will be somewhere to the right of 0. And we will also consider now other 2 points on the real line. 2L, which will be another positive number sitting to the right of L, and L divided by 2, which is a positive number to the left of L. Now, if An divided by Bn will converge to L, at some point we know that this ratio, An over Bl, will fall within this interval that goes from L divided by 2 to 2L. So we can say this, saying that definitively An over Bn will be less than or equal to 2L and larger than or equal to L divided by 2. Now we can multiply this inequality by Bn. In fact, we know that Bn is strictly larger than 0, so it doesn't change the inequality. So that we have L divided by 2Bn less than or equal An less than or equal to LBn. Now, if we, this is an inequality referred to the sequences. If we now build the partial sums of these sequences, we have that the sum of L divided by 2 Bn can be also expressed as L divided by 2 sum of Bn, because in fact L divided by 2 can be factored out from the sum. And this is less than or equal of sum of An less than or equal to L sum of Bn. We did the same trick. We just have taken 2L out of the sum. So this is still valid. And now let's see from this inequality what can we conclude. Well, you see that if we take the limit now as n goes to infinity, and we see that the series sum Bn, which is the limit as n goes to infinity of the partial sum, is diverging to plus infinity. Well, by looking at the left inequality, this one, we see that clearly this will push the series sum of An to diverge to plus infinity. If instead we have that the sum of Bn is convergent, well, then we will look at the right inequality, and we'll see now that the sum Bn will limit the sum of An to be convergent as well. So this is an easy proof of the criterion. So what is the operative procedure? How can we use this criterion? Suppose that we need to study the sum of An, but we struggle with this study because it is a series that we don't know how to analyze. The method of evaluating the limit of the partial sums doesn't lead us anywhere. So we look now for another sequence Bn such that An over Bn will converge to a positive number L. Of course, we need to be clever and find such a sequence Bn of which we know something about the series built on top of it. So we know what it will be the behavior of sum of Bn. We don't want to make our life more complex than already is, okay? So we want to simplify our job. So we will be looking at a sequence Bn that we know will create a series sum of Bn that we know how to study. Then we can conclude by applying the asymptotic criterion that the sum of An will have exactly the same behavior of Bn. Okay, now that we stated the standard version of the criterion, let's see what is the other version. So we still have criterion of asymptotic convergence, but now we'll call this limit case, okay? So this was the sorry, not convergence, but let me call this asymptotic comparison, because this is what it is, comparison. Okay, and well, the limit case is also using two sequences, An and Bn, An larger than or equal to 0 and Bn strictly larger than 0, and we are still analyzing the ratio An over Bn, but now this time we see that this ratio will converge to 0. If this happens, then we can only make a conclusion if the sum of Bn is convergent. That implies that the sum of An is convergent. Okay, let me prove this. We know that the sum, well, the ratio An over Bn will converge to 0. Okay, so that implies that definitively we have that this ratio, because it will get closer and closer to 0, at some point it will fall within the interval between 0 and 1. This is to say that definitively An over Bn will be larger than or equal to 0 and less than or equal to 1. And now, because Bn is strictly larger than 0, we can multiply out by Bn, and we get that An is less than or equal to Bn. And by just looking at this inequality, Well, by pure comparison, we see now that if the sum of Bn, if this series is convergent, well, this will limit the sum of An to be convergent. Instead, we cannot say anything if we have that the sum of Bn is divergent. We could have that the sum of An is convergent or divergent. So, no conclusion regarding that. Let's analyze the other limit case. The other limit case with the always the same hypothesis on the two sequences an and bn. Well, the other situation is that now the ratio an over bn will diverge to plus infinity. Well, in that case, we can conclude something only if the sum of bn is diverging to plus infinity. In fact, in that case, we can say that the sum of an is also diverging to plus infinity. Let's see the proof, which is very similar. Now we know that definitively it must be that this ratio will go beyond 1. So at some point an over bn will be larger than or equal to 1. And if we multiply by bn, we have that an is larger than or equal to bn, which says that the sum of an, of course, the partial sum is going to be larger than or equal of the partial sum of bn. And this implies that if sum of bn will diverge to plus infinity, this will push sum of an to diverge as well. If instead sum of bn converges, we cannot say anything about the sum of an. So you see that these two parts of this criterion of asymptotic comparison in the limit cases basically will deal with convergence and divergence in two different situations. So if we are lucky and we have that an over bn is equal to 0 and the sum of bn convergence, well, then we can conclude that the sum of an is convergent. If instead we have that the limit of the ratio is plus infinity and sum of bn will diverge to plus infinity, then we can conclude about the sum of an to be divergent as well. Now, let me explain why are we spending so much time in all these criteria. Well, the truth is that there are only a limited number of cases where we know how to study a series. And these classes of series are listed below. We have a first class, which is the so-called class of generalized harmonic series. So these series are a series of the type sum for n that goes from 1 to infinity of 1 over n to the a, where a is a real number. And the behavior of this series depend on a. If a is less than or equal to 1, then the generalized harmonic series will diverge to plus infinity. If instead a is larger than 1, we can say that the generalized harmonic series is convergent. And notice that we don't know what will be the numerical value of the sum, except the few situations. The only situation when a is an even integer. Only in that case we know how to evaluate the sum. For all other situations, we just know what will be the general behavior, convergent or divergent. So this is a first important class of series. So if we have one of these series, we can establish its behavior by just looking at the value of a. Another very close relative of this series is the following one, which I don't think has a specific name, but I mean, you realize what is the similarity, because this is the sum as n goes from 2 to infinity of 1 divided by n times logarithm of n all raised to the a. You see that it is very similar to the previous one. The only difference is that now we have this logarithm of n at the denominator, which is raised to the a, instead of having n raised to the a. Okay, and you see why we start from 2, just to avoid the singularity in n equal 1, because we would have logarithm of 1, 0 at the denominator. okay? And it turns out that the behavior of this system, of this series, depends on A in pretty much the same way. In fact, if we have that A is less than or equal to 1, the series is diverging to plus infinity. If A is larger than 1, the series is converging. Then we have the class of telescopic series, which we saw right at the start when studying series. And we saw that, well, the reality is that we have only a few cases of this telescopic series, so these are not very useful. Instead, what are very useful are the geometric series, and we also spent some time analyzing this series. So these four classes are basically the only series that we know how to analyze. How can we do with all the other possible series? Well, we can just resort to the comparison criteria, okay, or the criteria that we have analyzed. In particular, we have seen all the criteria for positive series. So if we have one series and we recognize that the general term of the sequence an is larger than or equal to 0, we can apply one of those criteria and compare to one of the known series so that we can draw conclusion regarding the behavior of this new series. So let me go into more details about the generalized harmonic series. In fact, we said that we gave this list of results, okay? So we said that if this is the generalized harmonic series, we can draw conclusion about the behavior depending on A being less than or equal to 1 or A larger than 1. Now we want to prove this, okay? We want to give evidence of this result. And to study an harmonic series, we have three tools available. The first tool is just using some ad hoc inequalities. So case by case, we will come up with an inequality and we will be using that inequality to study the divergence or convergence of the series. Another option would be to use Cauchy's condensation, and the third option would be using a criterion based on the comparison between series and integrals. Now, this tool will be introduced after discussing the integral. So we'll leave this aside for a while. We'll come back on this after introducing the integrals. But let's start and consider the most meaningful cases. For example, let's say A is equal to 1. Okay? Well, the generalized harmonic series become the sum as n goes from 1 to infinity of 1 divided by n, which is the harmonic series. And we will prove now that this harmonic series will diverge to plus infinity, which is consistent with the this result. Okay, we said that if A is less than or equal to 1, so in particular if A is 1, we would expect the harmonic series to diverge. And we will prove this now in many ways, okay? Now, the first way to prove this is just using the criterion of asymptotic comparison with one of the series that we know. And we will be using now one of the telescopic series that we have introduced in the previous lecture, namely the sum as n goes from 1 to infinity of the logarithm of 1 plus 1 over n. Okay, and we know that this series will diverge to plus infinity. We proved this. Okay, so we want to apply the asymptotic comparison with this being bn. So bn is the logarithm of 1 plus 1 over n, and instead an is going to be 1 over n. Let's see if all conditions for the applicability are satisfied. An, which is 1 over n, is larger than or equal to 0. Bn, which is the logarithm of 1 plus 1 over n, well, this is strictly larger than 0. In fact, if you remember the graph of the logarithm, because we are now, the argument of the logarithm is 1 plus 1 over n, so it is sitting to the right of 1, we know for sure that the logarithm is strictly larger than 0. So yes, we are, all the conditions are satisfied. So let's see what happens to the ratio an over bn. Well, but this ratio, of course, is 1 over n divided by logarithm of 1 plus 1 over n. And we need to evaluate the limit as n goes to plus infinity. Now, because we don't know how to study this sequence, we can resort to the function sequence criterion. You remember this criterion. When we are given a sequence and we don't know how to study that, we can transform the sequence into a function and study the function and draw conclusion about the limit of the sequence. Of course, we need to make a change of variable, and the change of variable that we make is that 1 over n, if n is a natural number, this can be also considered to be x, a real variable. So this limit becomes limit as x goes to 0, because when n goes to infinity, x goes to 0, of x divided by the logarithm of 1 plus x. But this is one of the fundamental limits. We know this to be 1, which is then a positive number. So we can conclude that the sum of an, which is the harmonic series, will have exactly the same behavior of the sum of logarithm 1 plus 1 over n. So we can say that the harmonic series will diverge to plus infinity. Let's now consider the case a less than 1. Well, the sequence becomes 1 over n raised to the a, with a less than 1. But we know that this fraction has a denominator which is smaller than n, right? So n to the a is smaller than n, because a is less than 1, which implies that 1 over n to the a is larger than or equal to 1 over n. So we can just apply a pure comparison, because we have that this inequality holds for every n into the natural numbers. So because we just proved that the harmonic series of 1 over n will diverge, we can conclude that the sum of 1 over n to the a will diverge as well to plus infinity. So this was easy. Let's now move to the case more interesting, where a is larger than 1. And we wish to prove that the sum as n goes from 1 to infinity of 1 over n to the a is convergent. Okay, so let's see how the partial sum of this series looks like. If we take Sn, okay, we need to add n plus 1 element. We'll start with n equal 1, and of course we have 1 over 1 to the a, which is 1. If we go for n equal 2, we have 1 over 2 to the a plus 1 over 3 to the a, up to 1 over n to the a. And because all the single terms are positive, of course this Sn is going to be larger than or equal to 0. So at this point we have only two possible behavior, right? So we know that Sn can diverge to plus infinity, or Sn will converge to some real number L. Okay, so there is no other possibility, right? We know that when we have a weakly increasing sequence Sn of partial sums, we have only these two possibilities. Now, if we want to prove that the series is convergent, so if we want to prove this, it will be sufficient to prove that Sn, which is exactly this in compact form, is bounded for every n. Okay, because if we prove that the sequence is bounded, it cannot be divergent, so the only option that remains on the table is that the series is convergent. Okay, so we would like to prove exactly this, that this partial sum Sn, which is the sum as k goes from 1 to n of 1 over k to the a, is bounded for every n. Now, we now can use an ad hoc inequality. You remember that we mentioned this, okay? We mentioned the fact that one way of studying generalized harmonic series is by just taking out of the hat some ad hoc inequality, and in this case the inequality that I'm going to use is Sn is less than or equal to 1 plus 1 over a minus 1 times 1 minus 1 over n to the a minus 1. So this is the inequality that I'm going to use now. And this inequality, if we manage to prove this inequality, well, we are done, because this inequality will prove that every partial sum is bounded. Now let me explain why this is actually a bound for every partial sum. Remember that we are in the situation where a is larger than 1. So if a is larger than 1, that means that a minus 1 is positive. Okay? And also the exponent of n is positive. But if the exponent of n is positive, that implies that 1 over n to the a minus 1 is going to be less than 1. So basically this parenthesis is going to be a number less than 1. So we can bound this right hand side of this inequality with 1 plus 1 over a minus 1, which is just a number. Okay? So this proves that for every n, every sum Sn will be bounded by this number. Okay, this is just a number. So that also proves that the series is convergent. Now you might wonder, where does this inequality come from? Well, it turns out that this will be quite evident after the introduction of the integral. Okay, but for the time being, I'll just give you an intuition about this inequality by just taking a specific example. Let's suppose that a is equal to 2. Okay, remember that a has to be any real number larger than 1. So a equal to 2 is the first real number larger than 1. So in that case, we have that Sn is equal to 1 plus 1 over 2 to the second plus 1 over 3 to the second plus dot 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 plus 1 over n to the square. Okay, so this is the sum of the first n terms of the sequence. Now let's have a look at this element here, 1 over 2 to the square. We want to build a bound for Sn, so we want to replace these terms with the larger terms. Okay, so because this term, which is 1 over 2 times 2, okay, so this fraction, right, so I'm considering now this term, 1 over 2 times 2. Well, this of course is less than or equal of 1 divided by 1 times 2, because I'm building a larger fraction by using a smaller denominator. Okay, now the same thing I can do. So basically this is the replacement that I'm doing. I'm replacing this with this. And I'm now going to do the same for 1 over 3 to the square. Well, 1 over 3 to the square is less than or equal of 1 divided by 2 times 3. And the same goes also for 1 over n squared. Is going to be less than or equal 1 divided by n minus 1 times n. So in general, I can write that Sn is less than or equal of the sum of all these terms. But I think you remembered where we encountered this, because this can also be re-expressed in more compactly as 1, this one starting 1, plus the sum as n goes from 1 to n of this fraction 1 divided by n times n plus 1. And this is just an example of a telescopic series. We prove that this series, the sum up to n, is equal to 1 minus 1 over n plus 1. So in conclusion, what we just proved for a specific case a equal 2, we have that Sn is less than or equal to 1 plus 1 minus 1 over n plus 1, which is a close relative to the original inequality. Okay, so in the original inequality we had that Sn is less than or equal to 1 plus 1 over a minus 1 times 1 minus 1 over n raised to the a minus 1. It's not the same, I know, but is very similar. It gives an intuition where all this come out. And we will prove this, we'll see how evident this will become after the introduction of the integrals. Okay, so let's say that now somehow we came up with this inequality. Well, we need to prove this inequality now. So the next step is going to be the proof of the inequality, and I'm repeating now the inequality here. We are saying that the partial sum for a generic n natural number, this is less than or equal of 1 plus 1 divided by a minus 1 times 1 minus 1 over n to the a minus 1, where a is a real number larger than 1. How can we prove this? By induction. So let's start with the base step for n equal 1. We have that S1 is equal just to the sum for k that goes from 1 to 1, we are just replacing n with 1, of 1 over n to the a. Well, but we have only one term in this sum, and this term is just 1. And we need to prove that this, if the inequality is true, this must be less than or equal 1 plus 1 over a minus 1 times 1 minus 1 divided by 1 to the a minus 1, because remember we are replacing n with 1. But notice that this is simply 0, right? So we are just left with the 1 that proves that the base step is satisfied. Now, the more complex thing is the induction step. So the induction step says that if the inequality is true for a generic n, and we have this is the hypothesis of the induction step, then we need to prove the inequality also for the next index, which is n plus 1. So we need to prove that s n plus 1 is less than or equal 1 plus 1 divided by a minus 1 times 1 minus 1 over n plus 1 to the a minus 1. Okay, I'm just replacing n with n plus 1 here. Okay, all the rest is the same. Now, the way to prove this last inequality is starting by building this Sn plus 1 from the hypothesis of the induction step. So what is Sn plus 1? Well, the definition is just Sn, the sum of the first n term, plus the n plus 1 term. But the n plus 1 term, of course, is 1 divided by n plus 1 raised to the a. This must be less than or equal to verify the inequality, right? We want to prove that this must be less than or equal to this. But now, before doing that step, let me use the induction step hypothesis, right? So by the induction step hypothesis, we know that this Sn, right? We know that this is the induction step hypothesis. Up to this point, we have just the expression of Sn plus 1 to be Sn plus 1 over n plus 1 to the a. But if we replace Sn with the right-hand side of this inequality, we can say that all this is less than or equal 1 plus 1 over a minus 1 times 1 minus 1 over n to the I minus 1 plus 1 over n plus 1 to the a. Okay, we can do that. I'm just replacing Sn with the right-hand side of the inequality. Okay, so now consider this. This is what we have got so far. So we have 1 plus 1 over a minus 1 times 1 minus 1 over n to the a minus 1 plus 1 over n plus 1 to the a. And we want to prove that this is less than or equal 1 plus 1 over a minus 1 times 1 minus 1 over n plus 1 to the a minus 1. Now let's make a few simplification here. What we can say is that, of course, this one and this one, they belong to both sides of the inequality. They will cancel out. And the same way we see that we have 1 divided by a minus 1 multiplied by 1 on the left hand side, and 1 divided by a minus 1 multiplied by 1 on the right hand side. So we just remove the 1 inside. So we are now left with this inequality, minus 1 divided by a minus 1 times 1 over n to the a minus 1 plus 1 divided by n plus 1 to the a, less than or equal minus 1 divided by a minus 1 times 1 over n plus 1 to the a minus 1, right? So this is what we need to prove. Now let's do something. Because a is larger than 1, we know that a minus 1 is larger than 0, right? And if a minus 1 is larger than 0, we can multiply the whole inequality by a minus 1. The equality will still remain valid. And what we get at this point is minus 1 over n to the a minus 1, because we just have simplified basically this a minus 1 in front. And the second term will become plus a minus 1 divided by n plus 1 to the a. This must be less than or equal minus 1 over n plus 1 to the a minus 1. Again, we can multiply the inequality by n plus 1 to the a minus 1, because this, of course, is another positive number. And what we get is minus n plus 1 to the a minus 1 divided by n to the a minus 1 plus a minus 1. By just simplifying the denominator, we are just left with n plus 1 at the denominator. This must be less than or equal minus 1, which is the only thing that remains on the left hand side if we multiply by n plus 1 to the a minus 1, right? So let's rewrite the first term as follows. We have a minus in front, and then we consider the common exponent a minus 1 of this fraction, n plus 1 divided by n. The second term is a minus 1 divided by n plus 1, which must be less than or equal to minus 1. And if we now reshuffle all the terms, okay, what we get is that basically this term, okay, we bring this term on the right hand side. What we have is 1 plus 1 over n all raised to the a minus 1. Well, this must be larger than or equal. We bring minus 1 to the left hand side, and basically we get 1 plus a minus 1 times 1 over n plus 1. So we need to prove this. If we prove this inequality, because all these are necessary sufficient condition, we go backwards and we'll prove the initial inequality. But this is nothing else than an example of Bernoulli's inequality. Remember, the Bernoulli inequality says that if you have 1 plus x raised to the m, okay, well, we can say that this left-hand side is larger than or equal 1 plus mx, where m is a positive, m is a real number, and this is valid for every x larger than minus 1. So we can just replace x with 1 over n and m with a minus 1, okay? And of course, because a is larger than 1, at this point we know that m is going to be positive, okay? But now it is easy to just replace this into the Bernoulli's inequality, and we get 1 plus 1 over n all raised to the a minus 1. This must be larger than or equal 1 plus m, which is a minus 1, times x, which is 1 over n. And because 1 over n, of course, is larger than 1 over n plus 1, it is even more true that this is larger than or equal 1 plus a minus 1 times 1 over n plus 1, which finally proves the inequality. So this will conclude the proof by induction of the inequality. Now that we have this inequality, okay, we know that every case is fixed for the generalized inverse. the generalized harmonic series. Because in fact, we just proved that if A is less than or equal to 1, the generalized harmonic series will divert to plus infinity, and if A is larger than 1, the partial sums, which are weakly increasing, are bounded. So the only option that we have is that the sum of 1 over n to the a is convergent. So that was an example of use of ad hoc inequality to study generalized harmonic series. We have another way of dealing with generalized harmonic series, which is the following method, which is called Cauchy's condensation. So let an be a sequence of real numbers that is made of positive or null terms. So an is larger than or equal to 0 for every natural number n. Remember that we are still in the class of positive sequences, okay? And we need also another condition to be satisfied, and the other condition is that an plus 1 is less than or equal an for every natural number n. So this is to say that the sequence of the terms is weakly decreasing. So we are dealing with a sequence like this one. It can remain constant or go down, but it cannot go up. Okay, so this is the condition for the sequence. And now we want to study the series that is built on top of that sequence. And this is the main statement of the theorem. If we don't know how to analyze the sum of an, we can instead study the sum as n goes to from 1 to infinity of 2 to the n multiplied by a with the index 2 to the n. In other words, we are now building a new sequence that is the original sequence evaluated only with indices which are powers of 2. And we multiply this sequence by 2 to the n. And we studied this sequence because for some reason this turns out to be easier for us. So if we can establish that this sequence is convergent, we can conclude that the original sequence of an is convergent, maybe with a different limit. If instead this sequence is divergent, we can conclude the same thing for the sum of an. So you see what is the power of this method. We start with the sum of an. We don't know how to do that because it is difficult for us to study that series. Then we can study in replacement to that the new series obtained by taking only the sequence of a with indices which are power of 2, and then we multiply by 2 to the n. If we establish that this series is convergent or divergent, well, the same behavior can be applied to the original series. Let me give you an example, and let's see how we can establish the convergence or divergence of the generalized harmonic series by just applying the Cauchy's condensation. So remember that in the generalized harmonic series we have an is equal to 1 over n to the a for some real number a. Okay? Now, let me check that the condition for the applicability of Cauchy's condensation are satisfied. First, we need to check that an, which is 1 over n to the a, is larger than or equal to 0. Done. Second, we need to check that it is a weakly decreasing series, but we have that 1 over n plus 1 to the a is less than or equal 1 divided by n to the a. So actually this is true if and only if a is larger than 0. But of course, these are the only interesting cases where a is larger than 0. You know why? Because of course if n equals 0, clearly the series will diverge because it will be 1 plus 1 plus 1 plus 1. Of course, this sum will diverge. But also, if a is less than 0, it turns out that the necessary condition is not satisfied, so the series will diverge anyway, right? So let's consider only the situation where a is larger than 0, okay? Okay, let's see what happens. we are now within the realm of applicability of Cauchy's condensation. And the criterion says, okay, you don't know what to do with the sum of 1 over n to the a. Well, you can study the sum as n goes from 1 to infinity of 2 to the n a with index 2 to the n, which is the sum as n goes from 1 to infinity of 2 to the n. And instead of writing 1 divided by n to the a, I will just replace n with the 2 to the n. But these can also be rewritten, the sequence can also be written as 2 divided by 2 to the a all raised to the n. And we recognize now that we have a geometric series. In fact, if we have that 2 divided by 2 to the a, which is the ratio of the geometric series, is larger than or equal to 1, which is just like saying that a is less than or equal to 1, we have divergence, because this is what happens for a geometric series. And you see that we are now back to the original scheme. Okay, this result is consistent with what we said before. If instead the ratio of the geometric series 2 divided by 2 to the a is less than 1, which is to say that a is larger than 1, we have convergence. This is again what we know about geometric series. Notice that the same criterion can be applied to prove the convergence, divergence of the sum of 1 over n logarithm of n raised to the a, right? So we can apply the Cauchy's condensation to prove the same result for that series. Now let's go to the proof of Cauchy's condensation, which is quite interesting as a method. So, proof of Cauchy's condensation. Let me start by writing all the elements of the sequence up to an index which is a power of 2. So we have a1, a2, a3, a4, a5, a6, a7, a8, a9, a10, a11, up to a16. So you see, I'm just stopping at a power of 2. Okay, actually this is what we can rewrite this partial sum as the sum of ak for k that goes from 1, because we start with a1, up to 2 to the n. And in this specific case, it turns out that n is equal to 4. Okay, so in this case we see that n is equal to 4 because the last index that we are considering is 2 to the 4th, which is 16. Now, the idea behind this proof is that we want to build two sequences, one that is larger and one that is smaller. But we don't just do this. We also want to split basically all the elements, all these first 16 elements, into groups. Each one of them has a number of elements which is a power of 2. Okay, so let me start by considering a first line that will separate the first element, a1. Okay, so this doesn't count. Okay, let me start with a2. Now, a2 is the first group, and of course this, how many elements in this group? 1, because this is the first power of 2, 2 to the 0. Now, the second group instead is going to be made of 2 elements, because this will be 2 to the 1 elements. So we have 2 elements in the second group. We will have 4 elements in the third group, because this will be the power 2 to the 2. And again, we have all these elements which are exactly 2 to the third. So we will have 8 elements in this third group. Okay? So we are splitting all the elements of the sequence AK into groups. We have a first group, well, this is some kind of outsider, we're considering this aside. Then we have a first group with the 2 to the 0 elements. Then we have a group with 2 to the 1 elements. We have a group with the 2 to the 2 elements. We have a group with 2 to the third elements. And of course we could continue to do this. But the important thing is that we stop at an element of the sequence with an index which is a power of 2. Now that we have done this, we go up and build a sequence which is larger. Now, the first element, well, we'll keep exactly the same element, A1. Nothing changes. Now, instead of A2, we need to pick now an element which is larger than A2. Remember that the AK sequence is a weakly decreasing sequence. So that means that A1 is larger than A2. So we can replace A2 with A1, which is larger. Now, if we want to replace A3, A4 with elements of the sequence which are larger, so an element which is larger both of A3 and A2, we can just replace them with A2 and A3. Let's do the same for the other group. So we have now 4 elements, A5, A6, A7, A8, and we want to replace them with one element of the sequence which is larger of any of them. But of course this element is A4. A4, A4, A4. And I think now you understand what is the idea of condensation. We are just replacing a group of elements with one single element. So in somehow we are condensating all these elements with the same number of elements all equal one to each other. The same thing happens with the last group. We have 8 elements, A9, A10, A11, up to A16, and we can replace all of them with A8, A8 up to A8, because this, of course, A8 will be larger of any of these elements. Okay, now that we have done this, let's go below and let's build a sequence which is smaller. Now, as always, the first element will remain the same, A1, doesn't count. Now, also for A2, we'll keep A2, right? You see why I'm not replacing with this with A3, because I want to keep the index of the element that is replacing all the other elements to be a power of 2. And in fact, notice that in this case we have A2, then we have A4, then we have A8. So all the indices of the replacing sequences are powers of 2. And we want to do the same with the smaller sequence. So we will keep A2 as it is. But in the next group, which is this group made by A3 and A4, we want to replace them with 2 elements which are equal, and each of these elements need to be larger of A3 and A4. For example, we can take A4. So now we have another group of 4 elements, A5, A6, A7, A8. We can replace this with the 4 elements which are larger, okay? Smaller. And these 4 elements will be A8, 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 A8. Same story for A16. Okay, now we are ready to write down the inequality. What is the ad hoc inequality that we are using now to prove this condensation criterion? Well, let me start by writing in the middle what is the sum that we are considering, right? This is the sum. Sum k goes from 1 to 2 to the n of ak. Now we want to build to the right something which is larger, and we want to build to the left something which is smaller. Okay, let me start with the larger one. So let me start with this inequality. So I will be considering now basically this, okay, the larger sequence. Well, this larger sequence can be expressed as A1. Okay, so this is A1, the first element. We'll keep this as it is. And then we can write all the other elements as we have groups, and the cardinality of each of these groups is just a power of 2. In fact, we know that the first power is going to be 2 to the 0. Okay, when k is equal to 0, we have 2 to the 0. The second group will have a cardinality 2 to the 1, which is exactly what we get if we replace k1, and then 2 to the 2, 2 to the 3, so this seems to be the right cardinality of each group. Now we also need to express what is the element contained in each of these groups. And we see that when k is equal to 0, right, we are having a 1. So we can express this as a with index 2 to the k. In fact, when k is equal to 0, we have a with index 2 to the 0, which is a1. When k is equal to 1, we have a with index 2 to the 1, which is a2. So this is correct, okay? So the right inequality is correct. Let's now try to build the left inequality, this one. So we are now considering this sequence, okay? The sequence of which is smaller than the given sequence. Now, the first element is the usual outsider, and we'll keep it a1. Then we have the first element is a2, just cardinality 1. So if I start with k equal 1, you agree that the first cardinality is exactly 2 to the 0, which is 1. Now for the second group, we have k equal 2, and we have a cardinality which is 2 raised to the 2 minus 1, which is 2. For the third group, we will have k equal 3, so we have 2 to the 3 minus 1, which is 2 to the 2, so it is 4. So this is the right cardinality for each group, and now we can write the element in each and every group. And the element when k is equal to 1, which is this situation here, right? This is for k equal 1. Well, for k equal 1, of course, we have a2. And in this case, we have k equal 2. And in fact, we have a with 2 raised to the 2, which is a4, and so on and so forth. So this inequality is exactly representing the same process, okay? The same thing that we have in this schematic representation. Let me re-express this in a different way, slightly different way. And what we get, I mean, we have a1, okay, so this is the first one, but instead of having 2 raised to the k minus 1 within the sum, I will take out 2 to the minus 1, which is nothing else than 1/2, that multiplies the sum as k goes from 1 to n of 2 to the k a with index 2 to the k. This must be less than or equal sum of k goes from 1 to 2 to the n of ak, less than or equal a1 plus sum k goes from 0 to n minus 1 of 2 to the k times a to the 2k. And now we are ready to go to the conclusion of this, because by just looking at the right inequality, if we have that this partial sum k goes from 0 to n minus 1 of 2 to the k a with 2 to the k, well, if this partial sum has a real limit, so it will basically, the series will converge, then we can say that also the partial sum s 2 to the n, okay, which is exactly what we have in the middle, the sum k goes from 1 to 2 to the n of ak, of course also this will converge, okay, by pure comparison. We have two sequences of partial sums. If the one on the right will converge, of course also the one on the left will converge. So that implies that s2 to the n converges. But because s2 to the n is a positive sequence, okay, we have all the partial sums are positive elements, and these are weakly increasing, the only possibility now is that s to the n is upper bounded. And if s to the n is upper bounded, well, certainly we also know that s to the n, s with n, is upper bounded, which proves finally that the sum of ak, which remember can only have other two possibilities, or diverging to plus infinity or converging, well, it can only converge, otherwise the partial sums would be unbounded. So this is the way we proved this. And if instead we want to use the left inequality, if we want to use this left inequality, well, suppose that studying the sum k goes from 1 to n of 2 to the k, a with 2k, this will diverge to plus infinity. Well, for the same reason, we have that s 2 to the n will diverge to plus infinity, which will push the sum of ak to diverge to plus infinity.